Example number 2 for rotational inertia, we have a figure shows a rigid body consisting of two particles of mass m connected by a rod of length L and negligible mass. It is important here that the rod has negligible mass, because if it didn't, then we would have to include it in our rotational inertia calculation. All right, so it doesn't, so we don't have to include it in our calculation. So for letter A, it says, what is the rotational inertia ICOM about an axis through the center of mass perpendicular to the rod as shown? So remember, when we have 2 point masses or just a point mass in general, our rotational inertia is just mr squared. So all we do here is find rotational inertia through the center of mass. It's just going to be, we'll call this M1 and M2. It'll be M1 R1 squared plus M2 R2 squared. Now R for both of these things, it's just the distance from the mass to the axis of rotation. You can see that the R for both is just 1/2 L. And the masses are the same also. So really all we get here is ICOM equals 2 times M times 1/2 L. And then we're going to square that whole thing because they're both mass M. Both R's are 1/2 L, so that's why I just have 2 times M times 1/2 L squared. Now, of course, when we square this whole term 1/2 L, we have to square both the 1/2 and the L. So we end up getting ICOM equals 2 times M times 1/4 L squared. 2 times 1/4 is 1/2. So what we end up getting here is ICOM equals 1/2 times ml squared. So that's our answer for letter A. Letter B says, what is the rotational inertia I of the body about an axis through the left end of the rod and parallel to the first axis? So since this axis is parallel, we want to use the parallel axis theorem. So parallel axis theorem is the new rotational inertia is equal to the rotational inertia through the center of mass, which we just found for part A, plus m times h squared, where m is the total mass of the system and h is that perpendicular distance between the center of mass and the new axis of rotation, which in this case is from here to here, which is again 1/2 L. So what we end up getting here is I is equal to I center of mass, which was 1/2 ml squared, plus total mass of the system. So really I should have written this as big M, not to be confused with those little m's, that we have 2 of those. So big M, total mass of the system, is 2m times h, which is 1/2 L, and then I'm going to square that. So again, when I square that whole term 1/2 L, I have to square both the 1/2 and the L. So here I end up getting 2m times 1/4 L squared. Again, 2 times 1/4 is just 1/2. So I end up getting 1/2 ml squared plus 1/2 ml squared, which ends up being ml squared. Just 1 times ml squared. And this makes sense, actually, because if we're looking at this axis of rotation right here, and we think about it in terms of just adding up, right? What we usually do, that at the very beginning, the rotational inertia at this axis of rotation equals m1 times r1 squared plus m2 times r2 squared. In this case, r1 is just 0 because it's at that axis of rotation, and r2 is L. So this whole term turns out to be 0 plus ml squared. So that's what our rotational inertia turns out to be when we have it through this axis of rotation right here, which we also found with that parallel axis theorem.